We've learned a lot of differentiation techniques, and we want to add one more to the list. It's called implicit differentiation. Before we can really work with implicit differentiation, it's important to know the difference between explicit and implicit form of an equation. Now, not every equation can have both forms. For instance, if we solve for, let's say, y equal 1 over x, this is explicit form. This is solve for y explicitly in terms of x, meaning I have all my y's on one side. In fact, I just have a single y on one side, and then everything on the right hand side is in terms of x. So this is an explicit form. Implicit form would be xy equal 1, meaning the x's and y's are mixed on a single side. So these are really the same equation. If you solve this for y, you get y equal 1 over x. This is its explicit form. This is the implicit form. However, sometimes we end up with some equations that we really can't do anything with in terms of rewriting. Let's look at something like x plus y cubed minus xy plus 4 equals 0. This is definitely implicit because I have x's and y's mixed, and there's no way I can get y by itself on the left and everything else on the right. So this is implicit form. I cannot solve and get it in an explicit form. So what we like to talk about with implicit differentiation is an equation, let's say, of this type that we have here in orange. How do I take the derivative of that? How do I find the slope of the tangent line of that when I can't get y equal stuff, if you want to think about it like that? So let's go ahead and look at taking a derivative of y equal 1 over x, and we're going to make sure we note that this is explicit. Well, the derivative, I'm going to think about this as two sides. The derivative of the left hand side would be y prime. Really, let's start thinking about that as dy dx. Remember, y prime and dy dx are the same notation. Now over here on the right hand side, I want to take the derivative with respect to x of 1 over x. So I want to take the derivative with respect to x of 1 over x. Now as we're simplifying here, the left hand side is dy dx, the right hand side is d dx. 1 over x I can rewrite as x to the negative 1. What that means is I flipped the denominator up into the numerator, so I had to negate the exponent. So here I have dy dx equals, now I go ahead and take this derivative. I bring the negative 1 down, I decrease the exponent by 1. And so this is how I take the derivative, and I get a solution here of dy dx equals negative 1 over x squared, because I'll flip that down into the denominator. So that's how I'd find that derivative explicitly. Now let's go ahead and do the same problem. Let's do the derivative of, let's do xy equal 1 implicitly. Of course, keep in mind that if I solve this for y, I divide both sides through by x and I get y equal 1 over x. So how would I find this derivative without solving for y? Now I could solve for y, I already did that problem right up above, but I want to say, what if I can't solve for y? How would I work this problem? Well, if I look at the left hand side, this is definitely a product, so I'll want to use the product rule. Okay, so the product rule would be the first times the derivative of the second. Now this is kind of weird because every time I usually take a derivative, it's always with respect to x. So here I want to think about this. I want to actually show my work here. So the first times the derivative with respect to x of the second, plus the second times the derivative with respect to x of the first, equals, and the derivative of 1, the derivative of a constant is 0. So let's run through that one more time. First times the derivative of the second plus the second times the derivative of the first. Now I have not taken the derivative yet. I've just kind of set out my plan here. Now if you notice, this dy dx, the derivative of y is 1. So the derivative of y is 1. And then I need to keep that dy dx because I'm taking the derivative of a variable other than x. So if this is the chain rule, the derivative of y is 1, the derivative of the outside is 1, the derivative of y is dy dx, the derivative of the inside is dy dx. Okay, plus y. And then dx dx, the derivative of x is 1. And then I'm left with the derivative of x with respect to x is 1. Now my whole goal here is to solve for dy dx. So take the derivative implicitly. And remember, I used the chain rule here when I went from here down to here. And really I'm using the chain rule here as well. But because I'm taking the derivative with respect to the variable of the same, it ends up working out just right and the dx over dx cancel. Okay, so now we want to simplify this. And you're going to say, I like the first method better, but sometimes we can't use the first method, and we'll see an example like that. So I have x dy dx plus y equals 0. So here I want to solve for dy dx. Okay, so I would subtract y from both sides. And I have x dy dx equals negative y. Divide both sides through by x. Show that canceling here. And I get dy dx equals negative y over x, which matches what I had up here. So derivative implicit and then derivative explicit. Now they don't look the same, but they will evaluate the same. Go ahead and note a couple things here. If x, y equal 1, and the only reason I can do that with this one is that I can actually solve for this. Otherwise I just have to leave it in this form, and it's okay in this form. They actually mean the same thing. But let's note, if x, y equal 1, y would equal 1 over x. And then if I plug that in here, in place of y, if I put 1 over x, I would get dy dx equals negative 1x squared. So you can see that they match from up here to down here, but this is its implicit derivative form. Okay, so that's kind of what I wanted you to understand, is the difference between implicit and explicit. Sometimes I cannot solve for an equation in terms of y alone, so I have to use implicit differentiation. Now when I use implicit differentiation, the important thing to remember is you always have to remember to take the derivative of the inside, and you always need to tack on that dy dx. And some people use y prime too. It kind of depends on how you learn to use implicit differentiation. So I like to use dy dx for my notation. The textbook might use, they might use y prime, but either way, make sure that you always tack on that derivative of the inside anytime you take the derivative with respect to a variable other than x that we're looking at. Let's go ahead and look at another example. Let's look at the one that we had before that I made up at the beginning. So let's look at x plus y cubed minus xy plus 4. Let me double check that. It doesn't really matter which one it is. X plus y cubed minus xy plus 4. Yep, that's it. Okay, so I want to find dy dx, find the derivative. And of course that derivative I'm going to note dy dx. So to get started here, I just take the derivative of x. The derivative of x is 1. Now I'm trying to find the derivative with respect to x, so I don't have to tack on the dx over dx, I can, dx over dx would just cancel. So just remember, whenever you take the derivative with respect to a variable x, I don't need to worry about tacking that on. This is where I need to worry about that. The derivative of y cubed is 3y squared. I'm taking the derivative of y with respect to x. Now again, if you wanted to write dx over dx here, you could, but it cancels. Okay, my next piece here I have to be really careful about. I need to put up my brackets because this piece right here is a product rule. So this would be the first function times the derivative of the second. The derivative of y is 1, and then I have to remember the chain piece, the derivative of y is dy dx. So first times the derivative of the second plus the second times the derivative of the first. The derivative of x is 1. Now again, if you want to tack on that dx over dx, you can, but it's going to just end up canceling. The derivative of 4 is 0, and I get equals 0 on the right because the derivative of 0 on the right is 0 as well. Okay, so important thing to remember here with the product rule, if there's a minus sign out front, make sure you have these brackets, and even if it's a plus sign out front, it's a good idea to make sure you have the brackets anyway, just so you kind of remember that. Now my goal here is to simplify and then solve for dy dx, but this rule or this step will be just to simplify. Okay, let's go ahead and have a look. Dx over dx cancels, so I'm just left with 1. 3y squared dy dx. Okay, now I'm going to distribute the negative, so I have minus x dy dx. Negative distributes over here, so I have minus y. Dx over dx is just 1 equals 0. So now what I want to do is solve for dy dx. Okay, so if I want to solve for dy dx, I want all my dy dx's on the left, everything else on the right. So I'm going to move the y across, and I'm going to subtract the 1 across. So it looks like I'm left with 3y squared dy dx. And again, an alternate notation to this would be a y prime in place of dy dx. And then on the right hand side I had y minus 1. So if you notice on the left hand side I have a common factor, it looks like, of dy dx. So let's go ahead and pull out that common factor. And if I factor out that common factor, I'm left with 3y squared minus x. Now if I want to solve for dy dx, I would divide both sides through by 3y squared minus x. Of course, on the left hand side these cancel, and I'm left with dy dx equals y minus 1 all over 3y squared minus x. There's my derivative. Now I never did solve for y. In fact, I can't solve for y here. This is an implicit form that cannot be changed to explicit form. So I could find the derivative anyway. So this is the slope of the tangent line at any defined point along a graph. I need to not only know x, but I also need to know y as the ordered pair. So the trick here, recognize the product rule, and then make sure you have the minus in brackets set up so you can make sure the negative distributes through when you're trying to take that derivative. Okay, let's go ahead and work through a few more of these. When we're working with implicit differentiation, you just need to remember that you're using the chain rule. Whenever you take the derivative with respect to a variable other than your variable of interest, you need to make sure you tack on that y prime or dy dx or dy dt or whatever your variable happens to be. So this one's pretty straightforward. Let's look at x squared plus y squared equals, let's do 16. So this is a circle with radius of 4 centered at the origin. So we want to find the derivative. And again, some people would notate the derivative y prime. I want to use dy dx. But again, y prime is appropriate to use here as well. So when we start with the derivative, I'm taking the derivative with respect to x, my variable of interest. The derivative of x squared is 2x. And then the derivative of x with respect to x is dx over dx, which cancels. Okay, so it doesn't make sense to put dx over dx, which just cancels every time. Now over here, the derivative of y squared is 2y, and now I take the derivative of the inside piece, if you want to think about it like that. I took the derivative with respect to a variable other than x, so I need to tack on that dy dx. And again, if you want to use a y prime there, you can. And the derivative of 16 is 0. So, next step would be to solve for dy dx. So simplifying, I want to get dy dx by itself, so I'd subtract 2x from both sides. And I'd have 2y, and of course I have that dy dx that needs to stay on the left, equals negative 2x. Divide both sides through by 2y. I have canceling occurring here. And I have dy dx equals, the 2's cancel, not the negative, but just the 2's, and I'm left with negative x over y. So this would be the slope of the tangent line at any point along this circle. Okay? Now one thing that we should kind of keep in mind here that I'll include is y cannot equal 0, because if y was 0, what would happen here is my slope would be undefined. So I have to be a little bit careful about that. I have to make sure that the denominator is defined. Now in this case, if the denominator was undefined, if the denominator was 0, I would have a vertical line. Okay, let's go ahead and throw in a problem with the trig function. And again, make sure that you're keeping track of your parentheses of your trig functions here. So for this one, let's go ahead and look at, let's do the cosine of xy. Always put parentheses around the arguments of your trig functions. I'm going to be looking for this on your handwritten homework and on your exams. And let's say cosine xy equals x plus y squared. So obviously I can't solve for y. I can't get only my y's on the left and only my x's on the right. So I'm going to have to use implicit differentiation here. And I want to solve for, I want to find dy dx. Now again, you'll see a notation of y prime used often here as well. Okay, so on the left hand side, I definitely have a chain rule with a product rule. Okay, so the derivative of the cosine is negative sine of xy. And then I need the derivative of xy. And that's where my product rule is going to come into play. So on the left hand side, I had the derivative of the cosine of u is negative sine of u, derivative of u. Now remember, u is some expression. Now I haven't taken my derivative yet, I'm just setting things up so far. And on the right hand side, the derivative of x is 1, and the derivative of y squared is 2y dy dx. Because I took the derivative with respect to y, with derivative of y with respect to x, dy dx. Okay, so now on the left hand side I have a little bit more work to do. I need to take that derivative. So I'm going to put up a big set of brackets because I'm going to have to use the product rule. So this is the product rule. So the product rule is the first function times the derivative with respect to x of the second function plus the second function times the derivative with respect to x of the first function. So first times the derivative of the second plus the second times the derivative of the first, and the first is x. And this equals, on the right hand side, 1 plus 2y dy dx. Now I can't solve for dy dx yet because I haven't actually taken the derivative on the left yet. So let's follow through and see what happens. Negative sine xy. Let's set up that big bracket. So I have x. The derivative of y is 1. I took the derivative of y with respect to x. I took the derivative with respect to a variable other than x, so I need to tack on that dy dx. That's the derivative of the inside, plus y. And the derivative of x is 1, but what's dx over dx is just 1. Okay, so now I want to solve for dy dx. Okay, so this will get your algebra skills going here. Okay, so it looks like to me we need to take this negative sine xy and distribute it. So we're going to have negative sine xy times x dy dx minus sine xy, so minus sine xy times y. Now again, you can see why it's so important that we put parentheses around the arguments of our trig function. I don't take xy times y. This is the negative sine of xy times y. Okay, so the y I can pop out front here in a minute. So I distributed through the negative sine xy, and this is equal to 1 plus 2y dy dx. Okay. I think I'm going to rewrite one more step here. Negative sine, I think I'm going to pull the x out front. Negative x sine xy dy dx. Okay, minus, I'm going to pull that y out front, minus y sine xy equals 1 plus 2y dy dx. Now remember, our key here was whenever we took the derivative with respect to a variable other than x, I tacked on that dy dx. So now when I solve for dy dx, I want all my dy dx's on the left, everything else on the right. So I'm going to add y sine xy, and I'm going to subtract 2y dy dx. So let's go ahead and write what we have here. So it looks like I have negative x sine xy dy dx minus 2y dy dx. Okay, now over here I had canceling occur, so it looks like on the right hand side I have equal 1 plus y sine xy. On the left hand side it looks like I have a dy dx that's in common, so I can go ahead and factor out that dy dx. And when I factor that out, I'll be left with negative x sine xy minus 2y equals 1 plus y sine xy. Now a couple things here, I think I've said this a lot, but please make sure that you always put parentheses around the arguments of your trig functions, just because if you don't, it gets really complicated here as to what's part of the trig function and what's not. Now to finish this off, if I want to solve for dy dx, I want it by itself, I could divide both sides through by negative x sine xy minus 2y. The minus 2y is not part of the trig function, so we don't write it like this. We have to make sure that we put parentheses around the trig function only. So on the left hand side I have canceling occurring, and I'm left with dy dx equals, I think I might want to pull a negative out here, so a negative sign out front, 1 plus y sine xy all over x sine xy minus, or sorry, plus 2y. And the reason that's a plus is because I factored a negative out front. So here's my derivative. Now another way I could write that is I could have distributed the negative through the top. And the reason I pulled it out of the bottom, it's pretty common if you have two negative signs somewhere that you would factor it out, especially if it's in the denominator. So this would be another form of that same derivative. Now all these problems we've been doing, remember, we're still trying to find the slope of the tangent line at any point along a graph. So let's actually do one of those problems. For this one, let's go ahead and find not just the slope of the tangent line, but let's go ahead and find the equation of the tangent line. So find the equation of the tangent line. To the graph, and notice I'm not saying to the function because this might not be a function, but to the graph. Let's do x squared. Let's have a quotient rule on this one. So let's do x squared plus x over y minus y cubed equals 5. At the ordered pair, let's do 2, 1. Now this point, 2, 1, has to lie on the graph. So if you want to check it, if you plug in a 2, I get 2 squared is 4. 4 plus 2 over 1 is 6. 6 minus 1 cubed. 6 minus 1 is 5. So this does lie on the graph. Now if this ordered pair didn't lie on the graph, then I couldn't write the equation of the tangent line. So to write the equation of a line, I need two things. I need a point and I need a slope. So let's go ahead and figure out slope. So slope is dy dx, or y prime. And again, you'll see either notation used. So let's go ahead and start by taking our derivative. This is definitely implicit. I'm not going to be able to solve for y in terms of x only. So the derivative of x squared is 2x. The derivative within, the derivative of x with respect to x is 1. So I'm taking the derivative with respect to the variable of my concern, so I don't need to tack on that dx over dx. Plus, now I have this quotient rule. So this piece right here would be the quotient rule. So I have to have up my big set of brackets because I'm going to put the entire quotient rule here. So the quotient rule starts with the bottom times the derivative of the top minus the top times the derivative of the bottom. Let me write that so you can read it. All over the bottom squared. Okay, so that's my quotient rule there. Minus the derivative of y cubed is minus 3y squared. I just took the derivative with respect to a variable other than x, so I need to make sure I tack on that dy dx. And of course the derivative of a constant is 0. Now, I think the first thing I want to do is work within these brackets to actually finish taking my derivative, because I haven't finished taking the derivative first. So I have y, and then the derivative of x with respect to x is 1. The dx is 1. So again, the bottom times the derivative of the top, the derivative of x is 1, minus the top times the derivative of the bottom, which would be 1. The derivative of y is 1 dy dx, and this is all over y squared. And of course I have my minus 3y squared dy dx equals 0. Now these, algebra is really important here, you can tell. I need to do a lot more solving here, but this is a different case. I don't need to really know what dy dx is right away. What I could do is I could start plugging in. So be really careful here that we kind of think about, do I need to find dy dx, or do I just need to find dy dx evaluated at my ordered pair 2, 1? So plug in 2, 1. Nowhere does it say that I can find dy dx in general. I can find dy dx at this particular point. So let's go ahead and plug that in. So I'm going to have 2 times x is 2 plus y times 1 is 1. Whoops, that's a minus x is 2. And of course I have that dy dx. I'm going to put that in a different color so we make sure we see it. And this is all over y squared. Well, y is 1, so this is 1 squared. Minus 3, y is 1 squared, dy dx equals 0. So this is a lot easier now to solve for 0 because now I have numbers instead of so many variables running around. So now we want to solve for dy dx. Now if you wanted to, you could have solved for dy dx first and then plugged in. So you can do either one here. Okay, on the left hand side I have 2 times 2 is 4. Now I'm going to split this up into two different pieces here. This will be plus 1 over 1. I can separate a fraction as long as I only have a monomial in the denominator. So plus 1 over 1 minus 2 over 1 dy dx. And I could have multiplied through by the denominator. Quite a few things I could have done there. Another thing I could have done is I could just look at 1 squared to get 1, and that's really the same as just a 1 in the denominator and split that out. Okay, minus 3 times 1 squared is just minus 3 dy dx. And of course this equals 0. Okay. So it looks like to me I have 4 plus 1 is 5. So 4 plus 1 is 5. And then I have a minus 2 dy dx minus 3 dy dx is going to be minus 5 dy dx equals 0. Okay, I want to solve for dy dx. Whoops, let's leave that in orange so we get that connection. So I think that I'll subtract 5 from both sides. And I get negative 5 dy dx equals negative 5. And again, divide both sides through by negative 5. I get canceling to occur. And I get dy dx equals negative 5 divided by negative 5 is 1. So this is not my slope of my tangent line at any point. This is my slope of my tangent line at the ordered pair 2, 1. So I'm going to write that a little bit different. Equals 1. Now what this notation means, dy dx evaluated at 2, 1, which is what I just did. And I got the slope is equal to 1. So this is my slope. So I have a slope of 1 and I have an ordered pair of 2, 1. Now your calculators, if you have an implicit form, calculators won't graph implicit form. So you're kind of stuck there with the calculator part. Some online calculators will, like Wolfram Alpha or Mathway or Desmos will, but your handheld calculators usually do not graph an implicit form. They need to have everything solved for y. So equation of the line. Okay, so remember my slope is 1 and my ordered pair is 2, 1. So I start with my point slope form, y minus 1 equals 1 times x minus 2. So if you were asked to leave your equation in point slope form, that would be your answer. Now if we wanted to go for slope intercept form, I would just go ahead and distribute the 1 and I'd have x minus 2. I'd add 1 to both sides and I get y equal x minus 1. Now these, if I were to graph these lines, they'd be identical. They're just different forms of the same thing. So this is called the slope intercept form. Now the reason it's called the slope intercept form is by looking at it, I know the slope is 1, the coefficient in front of the x, and the y-intercept is negative 1. Now there's one other form that comes up sometimes, not as often. So for standard form or general form, what we do is we move everything to the left. So if I subtract x and add 1, subtract x and add 1, on the left hand side I have a negative x plus y plus 1 equals 0. Now usually we like our leading coefficient to be a positive one, so a positive x in this case, and so if I multiplied through I'd get x minus y minus 1 equals 0. This is called standard form or general form. So these are all different forms. Now if you were to graph each of these, you'd get the identical line. They're just different forms that you can look at when you're looking at graphing a line. You can also take higher order derivatives using implicit differentiation as well. When you're working with higher order derivatives, you just need to make a substitution in the second derivative to get going. So let's go ahead and find d squared y dx squared, or y double prime, the second derivative of, and let's throw a trig function in here. Let's do x plus y equals sine of y. Now again, please put parentheses around the arguments of your trig functions. So let's go ahead and get started finding our first derivative. Because to get to the second derivative, you need to start with the first one. So the first derivative, the derivative of x is 1. The derivative of y is 1, but I took the derivative with respect to a variable other than x, so I need to tack on that dy dx for our chain rule, equals the derivative of sine is cosine of y times the derivative of y. So this is our chain rule again, derivative of y with respect to x. So on the left hand side I have a 1 plus dy dx equals the cosine of y. Now the derivative of y is 1, so that's what this notation is meaning. It's saying take the derivative of this function with respect to x. The derivative of y is 1, and then when I took the chain rule, I need to think, oh, I took the derivative of y with respect to x, with respect to a variable other than x, so I need to tack on that dy dx. So let's go ahead and rewrite. I have 1 plus dy dx, and again you might see a y prime here as well, equals cosine of y times dy dx. So if I want to solve for dy dx, I need to move everything over to the left. So I want to solve for dy dx. Okay, so I think just to make things easy for me, I like the variable that I'm trying to solve for on the left. So I'm going to multiply by minus cosine y, or I'm sorry, I'm going to subtract minus cosine y dy dx, and I'm going to subtract 1 from both sides as well. Good old algebra. Okay, so everything cancels here and here, and I very carefully need to write what I have left. I have dy dx minus cosine of y dy dx equals -1. So I can see that my common factor over on the left hand side is that dy dx. If I factor out dy dx, I'm left with 1, because I factored the dy dx away. There's an implied 1 remaining there, minus cosine of y equals -1. And then to finish, I divide both sides through by 1 minus cosine of y. Of course, whatever you do to one side, you do to the other. And I have canceling occurring here. And I'm left with dy dx equals -1 over 1 minus cosine of y. Now this is not my answer yet. This is just the first derivative. So remember, I'm trying to find second derivative. So this is the first derivative. These will really test your algebraic prowess and give you lots of practice. So continuing on with the same problem, now I'm going to find the second derivative. So I'm looking at the left-hand side, and I'm starting with the derivative with respect to x of dy dx. So I'm just looking at the left-hand side here, is equal to the derivative with respect to x of negative 1 over 1 minus cosine of y. So on the left-hand side, I have my second derivative. D times d, d squared, y dx squared. So that's my notation that I'm looking at. And then on the right-hand side, I see several things that we could try here. I definitely see a quotient rule that we could do, the bottom times the derivative of the top minus the top times the derivative of the bottom. I also see that we could pop this up top and put it to the negative 1 power and use a chain rule. So it kind of just depends on what your preference is. So if you would rather solve this in a different way than I'm about to, that's okay. I'm going to rewrite and use a chain rule on this. So I'm going to have 1 minus cosine of y. I'm going to pop that up top, and that will be to the negative 1. So this I'm popping up top to the negative 1. And then I also have to remember I have a negative sign out front. So there's a lot going on there. So here is my derivative on the left, d squared y dx squared. This means second derivative. Now when I take the derivative here, I have a negative out front. I bring the negative 1 down. I decrease my exponent by 1. So this becomes a negative 2. And then I need to multiply it by the derivative within. So again, this is that chain rule. Now I'm not taking the derivative within right now. I'm just noting that I'm going to take the derivative within. So this is the derivative of the outside in the green, derivative of the inside in the orange. Okay, rewriting, I have d squared y dx squared equals negative times a negative is a positive, so I can just drop that notation. And then I have this 1 minus cosine of y to the negative 2, which I think will eventually flip. And then over here, this is interesting, the derivative of 1 is 0. So I'm just going to leave that as a 0. I'm going to show that as my placeholder here. In the derivative, I'm going to drag along the minus sign. The derivative of the cosine of y is the negative sine of y times the derivative of y with respect to x. So the minus sign is right here. The derivative of the cosine is a negative sine of y times the derivative of y with respect to x. Okay, so not done yet. D squared y dx squared. I think I'm going to leave this still one more step before I flip it. So over here, I have a 0 minus a negative is the same as a positive, sine of y, and then dy dx. Now remember, I am trying to solve for d squared y dx squared, the second derivative. And it looks like I've done it, except this dy dx looks to be a bit in the way. I know what dy dx is from up above. Dy dx was negative 1 over 1 minus cosine y. Let me double check, make sure that's right. Negative 1 over 1 minus cosine y. Yep, that's right. So I'm going to substitute that in. So let's go ahead and keep writing and simplifying. D squared y dx squared. And I think I'm going to flip this now. I'm going to rewrite this as 1 over 1 minus cosine of y quantity squared. I have to have these brackets up. And then over here I'll have times sine of y. And then I'll have that times that dy dx. And that dy dx was negative 1 over 1 minus cosine of y. Now we have a lot going on here, but I think I can simplify quite a bit. D squared y dx squared. Multiplying straight across the top, I have a negative sine of y. In the denominator, I have 1 minus cosine y quantity squared times 1 minus cosine y quantity. is going to be 1 minus cosine of y cubed. And there is finally my second derivative. Now, technically we could take a third and a fourth derivative, but you can see how complicated that these get. So make sure when you're looking at these that you show all your work. Don't drop any steps. It's going to be really important because there's a lot of algebra going on here. And again, this is higher order derivatives. This is second derivative. Okay, I don't think we have too much time for one more, although that would be fun to do. But I do want to make one more quick note. Sometimes in your homework and in your handwritten homework and in your exams, it'll refer to a line that is a normal line. Well, a normal line is basically a line that's perpendicular to a curve at a point, and that point's tangent line. So a normal line, let's say we have a graph, and let's make it a curve that's kind of easy to work with. And the point that I'm interested in working with is this point, let's say AB. So if I wanted to talk about the normal line at the point AB, what I would have here is this tangent line. So this is my tangent line. And then the normal line would be the line that was perpendicular to this tangent line going through this point. So this is at a 90-degree angle. This is the normal line. So if you look at these two lines, the tangent line and the normal line are perpendicular. Okay? So again, tangent line and normal line are perpendicular through this point. So what is true about a tangent line and a normal line? They have negative reciprocal slopes. Because remember, two lines that are perpendicular have slopes that are negative reciprocals of each other. So let's go ahead and write that down. It'll be an important thing to know. So we could say here a tangent line and its normal line have negative reciprocal slopes. Trying to avoid another page here, but I'll open up a new page for a quick example. So let's say the slope of the tangent line. So I'm going to say tangent, let's do it this way. Let's do slope of my tangent line, let's say was 2/3. That would imply the slope of the normal line would be a -3/2, negative reciprocal. So let's look at another example. The slope of the normal line, let's say, was -2. The slope of the tangent line is a negative reciprocal. So let's think about this as -2/1. So the negative reciprocal, this would become a +1/2. A couple more. Let's do the slope of the tangent line. It's 0. This means that the slope of the normal line is undefined. So let's think about that. 0 could be 0/1, 0/2, 0 over some number. I'm just going to choose 1 for this example. And when I flip it, it becomes 1/0, and I negate it, it becomes a -1/0. Either way, it's undefined. So what's happening here then is this is a horizontal line because my slope is 0. So the line normal to that, of course, would be this perpendicular line to this would be undefined slope. This is a vertical line. And this horizontal line has a slope of 0. So this is an important connection to remember. And again, normal kind of goes after that idea of perpendicular, but it's perpendicular to the tangent line at a particular point, in this case AB. Good luck as usual. If you have any questions, please let me know.